Hello everyone, my name is Stephanie Broxton and welcome to the Smarter Together webinar series. This webinar series touches upon how multidisciplinary applied research can be used to make a community impact and improve the human condition. I'm delighted this week to introduce some ongoing research surrounding autonomous Aerotropolis digital twin modeling. I have the great pleasure of introducing to you Dr. Dimitri Mavris and Dr. Perry Yang from Georgia Tech, who will introduce and discuss this research. After their presentation, we will welcome our other panelists to add to the discussion. As we know, Hartsfield-Jackson Airport and MARTA are both critical infrastructures when evaluating the complex nature of the Aerotropolis. To that end, we have with us today Dr. Kirk Talbott, the CIO at MARTA, and Kenneth Williams, the Airport Transportation Systems Director at Hartsfield-Jackson. Finally, we will have a Q&A session with any remaining time. Please remember, we welcome your questions in the corresponding Q&A area throughout the presentation. I'm just going to share the PowerPoint. And you guys can take it away whenever you're ready.
Okay, good afternoon, everyone. This is Dimitri Mavris. I'm from the School of Aerospace Engineering. And in this case, I'm not really speaking to you as an aerospace professor, but more of a system engineer and system architect. And this is a very unique endeavor. Very rarely you see different departments and colleges mixing together. So this is a joint effort between the system integration, system analysis, and the College of Design, which is under the School of Architecture and City and Regional Planning. So we're splitting the presentation between myself and Perry Young, who will come right after me, and then I'll come at the end to close it out. So if we go to the next slide. The theme for today is smart cities as an engineering system design. We are moving towards what we refer to here as an autonomous Aerotropolis, digital twin. So if we go to the next slide. Just to give you a little bit of context, let's start with the vision for what is a smart city. So maybe we can click a couple of times. We start seeing a tremendous growth all around the world. The population is increasing very rapidly. I think right now we stand at 7.7 billion people. We see urbanization growth and population metropolitan areas is very rapidly rising. But when you have that kind of migration, you have a whole bunch of challenges that need to overcome. Could be from public safety to the cost of living, to pollution levels, to aging infrastructure, to congestion, and so forth. So one of the enablers and one of the hypotheses that maybe this is a way to go forward is through this concept of smart cities. So smart cities are urban areas that use different types of data to manage assets and resources, to improve efficiency, and they do this by bringing together technology, government, and society to deal with all those problems in an interdisciplinary type of way. So the word smart in this case is through capabilities enabled by advanced data analytics. Issues associated with urbanization growth can be addressed more efficiently by having this ability to solve these issues very, very rapidly and over time autonomously without a human in the mix. You go to the next slide. So when you start thinking of this now, you're talking a massive system of systems, and that's actually how I got involved in this one through research in system of systems. So there is no single perspective or strategy that can change the shape of a city, only shared knowledge and collaboration combined with foresight, shared long-term goals, coordinated short-term actions, and continuous measurement and feedback over many areas of change. So what you see over here is a system that's a giga type of problem in terms of all the connectivity that it has. And if you look at the number of systems involved, they're 10 to the 9 order. So it's a massive, complex problem that up to this point we did not have the capability of actually even consider modeling and handling. Go to the next slide. Yeah, next slide.
Sorry, everyone, I'm experiencing a delay in clicking the slide.
Okay. Well, maybe we can admire the art in the meantime.
There we go. So sorry.
Okay, no problem. So when you take that very complex system and you break it down, you really see that you have three different perspectives. You have the physical world that we live in, you have the cyber-physical world, and then you have this computational world. And those three things are kind of working with each other. So if you look at the arrows on the left-hand side, the more high up you go, it's more abstract. Of course, as you go down, go more towards the more concrete perspective, and that's where you see conventional engineering. But those three things do have to come together, and all this connectivity has to be addressed, and then figure out how to harmonize it. If you go to the next slide. So the Aerotropolis now is one of those potential use cases. So we put it over here as the ask. So the motivation is to address spatial mismatch of housing affordability and job location, improved inclusiveness in urban mobility and public transit systems. The objective of the study that we're working together with Perry and our partners is to identify enabling concepts and technologies on autonomous mobility to improve traffic, adapt to the demand in an airport city type of a setting. An airport city here would be an airport plus the surrounding cities and the business districts. Explore data-driven approaches for operations optimization, mobility modeling to support efficient driven decisions for both tactical and strategic planning. So ultimately, the goal here of this endeavor will be a system of systems level analysis to support decisions on mobility planning to further boost social inclusivity and reduce mismatch between housing affordability and jobs. So we had a group of students from both the departments kind of thinking of this over the last several months. So some of the challenges that have been identified is that, of course, under mismatch, there's a mismatch between housing affordability and jobs. There is a non-inclusive mobility component, example, schedules and routes that don't effectively serve traffic and demand. And then we have the impact of disruptions, the continuity of services and access during the COVID pandemic would be a scenario like that. Go to the next slide. So the background behind this Aerotropolis project, starts with the concept of an airport city. The airport city is the inside the fence airport area of a large airport, including the airport. So that includes terminals, apron, and runways, and on airport businesses such as air cargo, logistic, offices, retail, and hotels. And the airport city is the core of the Aerotropolis, a new urban form evolving around many major airports. Zooming in now to Aerotropolis Atlanta, it's a planned mixed-use development in Hayville, Georgia, on the site of the former Ford Atlanta assembly plant, and the site is directly adjacent to the airport. The complex is to house offices, retail, and entertainment. And the Aerotropolis Atlanta CID, Community Improvement District, are local control quasi-governmental entities established by provision of the state, and they're empowered to serve as the means of funding, beautification, public safety, infrastructure projects. Those are some of the partners of this exercise. Go to the next slide. So trying to scope the problem we're here, before we get to the actual city, is to do some experimentation, if you like. In this case, it will be a virtual experimentation. And the idea is to maybe base this on a campus. And Georgia Tech has invested over the last few years with my lab to actually create such a digital twin of elements of the infrastructure. So now it's an opportunity here to start utilizing some of these lessons learned as we're extrapolating it to this problem. So here we're talking about modeling and design at the city level, benchmarking and understanding the systems without dedicated support by the experts. And then technologies and enablers are hard to be proven and showcased at the scale of a city. So the use case here of this campus is a test bed for the development and demonstration of all those concepts. And as you see over there, it kind of takes a portion of the city, if you like, tries to map it either at the campus level as a big chunk of series of buildings, or even zooming in at a specific building. And there has been research at both levels. You go to the next slide. So let's talk a little bit about this use case. It started about 6 years ago when the Chief Business Officer of Georgia Tech approached us with the idea to take some of the work that we're doing in aerospace and in Navy work and actually take advantage of the plethora of information and data that has been gathered by all the sensors and all the buildings around the campus. And then initially started just like a mechanical, electrical type of a problem, but as you see over there, Georgia Tech is made out of many, many layers of systems. And progressively, as the years progress, we try to tackle different elements of this one. And then the desired qualities over there was to show that it's a sustainable campus, that it was resilient to fluctuations in weather and energy, emergency events, even cyber threats. And then it was adaptable, and one of the key things there, of course, was that the campus continuously grows. So no matter what model you build, it's almost in a constant need to keep on being updated. With the next slide. So we took this plethora of data, as we said, and the very first thing was to work with the engineers on campus, that they're actually knowledgeable about this information, they had access. There had to be an element of cleaning up the data, coordinating it, automating it, and the like. And then the idea was to represent elements of the real artifact with a computational model. Initially, it was a data-driven approach, and then progressively the data was used to actually calibrate models so you can do forecasting and predict things that they were not already observed and recorded through the years of data that they were gathering. The next slide. So slowly, we started mapping it to the appropriate area. So on the left-hand side, you see the real world, and on the right-hand side, the digital twin of this thing. So it starts as a model representation. As the data gets collected, it gets calibrated. But then as it progresses over time, there is a need for continuous updating, and you will see later on we're at the point right now that if you put buildings side by side, instead of treating them on a statistical average, they have a very unique fingerprint of a behavior. And then it kind of shows below, the types of data that was gathered, the analytics that was done on it, the modeling simulation, and then on the right-hand side you see this system of systems sliced into layers. At the very top you have a geographic information layer. Then you have a traffic and mobility layer, an energy layer for the HVAC, and one for the electrical grid. Then you have the security layer, and then you have the campus services. Okay, so this is 6 of those slices. The next slide. So as we started laying it out then, the next thing that we encountered was that depending on who you're talking to, they have different perspectives, and the models cannot always be the same. So the first slice is to do this based on objective and based on a timeline. So if you look at present and near term, most of the objectives are directly linked into taking an existing campus and improving it as it is. So the objective there is to run the campus efficiently, avoid costs, energy savings, and provide reliability and safety to the system. As you're moving forward, you're going more into a forecasting mode. You're trying to figure out, how these decisions need to be substantiated. So you're looking for a data-driven and forecasting, scenario-based approach to decision-making, and trying to rationalize the decisions that they will be made by the decision makers. Go to the next slide. So again, taking that same thing. So the first phase then is dominated by situational awareness and operation optimization. So a series of tools were created to explore the data, benchmark the performance, detect the faults and degradation, forecast loads, and explore alternative operations. Then a separate set of tools for the forecasting, especially when it came to new approaches, new technologies, and the like. And then some kind of CBO, tabletop type of capability to do big time adjustments into the landscape of the campus in terms of what buildings and the like. And also the very last one shows here a depiction where you start looking about environmental sustainability and carbon commitment of some kind of a carbon neutrality. So identifying where these benefits will come from, and this was an idea from the work that we do in aerospace for ICAO. You go to the next slide. So one more click. So there are 3 different levels here, just to familiarize you with it. There is the macro level, and that is when you look at the campus as a whole, and you can play games at that level. When you go into the data that feeds into this one, you're in the mesoscale, so you have about 20,000 different streams of data. And then if you go down to the specific building, now you're adding another 10,000 or so endpoints with internal data per building. So the number of sensors blows up exponentially as you start going from a macro level to a meso to a micro level depiction of the campus. So we started trying to do the meso macro, and then we have specific examples, like the Candida building was one of them, that we went down into the building level. Go to the next one. So this is a depiction of a dashboard that was created. Imagine this thing is covering a huge wall in the Weber building where we have our visualization facility. What you see over there is a series of slide bars and metadata that you can click and see the ages of the different buildings, the networks, and then you can identify on the left-hand side right now, it's isolating the kilowatt hours as it pertains to electricity. The little dial has pulled in all the data for a specific year and a specific month. And then this color coding from almost magenta to red to yellow is a Pareto plot that shows which buildings are actually consuming the most at that specific point in time. So then you can dial it in, for different months. You can put it side by side. And then on the right-hand side over there is where you start now, maybe finding a specific sensor and trying to figure out how it's trending. If you click again. So just to show you some results over here, this is a building on campus. It's actually the Weber building, and it kind of shows the raw data on the left-hand side. It kind of shows the amount of cooling on both a summer and a winter day. So you can see it's a big fastball. You can't tell a thing. The very first thing was to clean up the data, and when you clean it, you start seeing a very distinct pattern. Blue one is indicating winter type days, and the orange is indicating hot days. And the very first observation is you start scratching your head. It's like, why are we cooling the building the winter time? And why is it operating like this 24 hours a day? So forth. And that is, again, a remnant of a technology that it was dual use, and most of the old buildings kind of have that. So if you click again, then you extrapolate this as an example here, extrapolating this to a variety of different buildings. The building that I was just mentioned to use the 4th column. And then you start seeing that some buildings, especially newer ones, that they were created with that mentality, that kind of thinking. They have very little consumption in the winter. So if you look at the CRB, the tiny little ball of blue in the middle, and then the orange is what's happening in the summertime. And around 6 p.m. to 6 a.m., where most of the people go home, there is no need for me to be cooling the building the way I ordinarily do it. So it kind of shows you again that they're not two buildings that have the same signature. And that's what I meant, that when you're creating a digital twin representation, you're not dealing with this on a statistical basis. You're actually looking at each and every one of the components and see how they have evolved, how they're being utilized, and then, that building itself is almost a system of systems. If you click again. So I'm going to pass it now over to my colleague to take us now from this point forward into the storytelling.
Yeah, thank you, Dimitri. This is Terry Yang from School of City Regional Planning and School of Architecture. Let me share with you how we started that this collaboration between College of Design that I'm part of this industry, like architecture, city planning, urban development. When I first listened to Dimitri's presentation, I was very impressed how aerospace engineer design campus. That's amazing. So I had a joke. They use the technology for sending human to Mars to design something on this planet. So we see campus as a complex system. So they use digital engineering system design to look at this problem. And so I would like to bring in another perspective from urban design, or from system design perspective, to look at this problem. So we would like to talk about Aerotropolis at the beginning as an urban economic development engine. And there's a social equity issue behind. We talk about spatial mismatch between the job, housing, affordability. And there's an important issue we'd like to address. How do we design the post-pandemic airport city? I think there's a major challenge we are facing. So urban design sees smart city as a system design. Using data-driven approach, we use analytics. We have this decision platform. So that's something I like to outline today. Next slide. So Aerotropolis, we see with our airport, it's becoming a global center in a way. And many global cities are turning their city airport into airport city, in which city centers are built around those globally important airports. You can see like Doha, Hong Kong at the left-hand side. You see Amsterdam, Schiphol Airport, Manchester. So those, I think airport city is a very interesting urban setting. You get around huge amount of people flowing in and out. To a certain degree, it's an urban center. So in terms of the amount of passenger kind of concentrated in that particular area, is a city, is a small urban system. And there's a legacy in this Atlanta Metro, ARC, and Aerotropolis. Atlanta has been working on this idea. How do we align the resource from the region to look at airports asset and provide a framework for strategic planning and development? Next. So Aerotropolis, as we discussed, in Atlanta, we are very proud of being in this largest hub in the nation. So there was 110 million passengers in 2019. So in average, you got 300,000 people coming in and out every day. It's much bigger than 5 Point, for instance. So it's a city center. And we have AACID as a key stakeholder. They are handling several territories around the airport. And MARTA is important. MARTA operates 2 rail stations on this side. There are 13 bus routes within this same CID area. Next. So this airport setting aggregate lots of potential industry and business. So it's a job center. So in the Aerotropolis Atlanta blueprint that was published in 2015, there was an idea called Blueprint Compass. So there is a tool for showing the shared interest of multiple stakeholders or industry that would come to Aerotropolis, including aerospace, logistics, food industry, multimedia, and life science. So there's so many opportunities for the city and the community. And next slide. And it is also facing some social issue. So in our research, we have observed some equity issue. So you can see within 5 miles or 10 miles radius of Atlanta Airport, you can see the distribution of those low-wage jobs around the airport, and where people live, right? Around the airport, people spend a lot of money to travel to from home to their job. So there are lots of neighborhood and community people. They spend more than 40% of their income in their housing and transportation. And within this area, you can see a lot of like kind of public transit desert. Many areas, they are outside of half a mile distance from transit transit stop, including MARTA railway stop or bus route. So there are 5 locations we have identified that with that issues. Next slide. So with that issue in mind, economic opportunity and social challenges, how do we look at this new issue about post-COVID-19 airport city, when city airport is so run down around the world? And how do we reconfigure airport and the surrounding urban environment to become safer, cleaner, and nimbler urban system? And that should be resilient and adaptable to those attacks or shock from pandemic or other system disruption. So you can see this is kind of diagram we drew in the workshop. And what about we bring in PRT system, on-demand, autonomous vehicle connecting domestic and international terminal, and there are lots of area like parking spaces. If you have AV system, lots of parking spaces can be reconfigured, repurposed. Can we redesign some of the area like outside of or in between the College Park and Airport MARTA area, and to redesign a future airport hub for those opportunities? And we know AACID and airport and Hartsfield-Jackson Atlanta Airport, they are investigating the possibility to bring in PRT, people rapid transit system. So what is that vision that we can jointly move forward for both the airport and also the community around that? Next slide. So with those issues in mind, the approach that Professor Telemetry Marvelous, which he just introduced to us, using digital twin system, can we address the issue from descriptive problem, like what is happening, to some diagnosis, like why did it happen, to the predictive model using big data to understand what is likely to happen in order to come with prescription or strategy for the future, how to act in response. So this is the model from aerospace engineering colleague. And next slide. And I was surprised to see how kind of it's identical to urban design, urban planning. So the left-hand side is the model. As urban designer, when we deal with complex system, we ask the same question: what is happening? How do we visually understand the transportation, built environment, water system, and so on? And what did that happen? How was it? How was the system functioning right now? And what is likely to happen through urban design? So urban designer suggests future scenario, and we like to understand how those scenarios would work for the community, work for the key stakeholder and local resident. And so we come with a decision model to ask the same question: how to react in response to those issues. So there's a strikingly similar ways of thinking that we can see from the two disciplines, aerospace engineering and urban design and city planning. Next. So let's show you a few examples that we did in other urban contexts. This is the project that I did in Tokyo, Japan, with the University of Tokyo and metropolitan government entity to look at how traditional urban community would benefit from the new technology, IoT, big data, AI, machine learning, analytics kind of method. Can we understand, say this is 37 million population, big metropolis, so there's a huge amount of data. How do we capture them and turn them into problem formulation for possible solution? Next slide. So we use this idea to look at complex system. So at the bottom, you have all kind of data. They are structured, they are unstructured. Can we come with algorithm and performance index for understanding heat wave attack, energy problem, flooding, carbon emission, visual quality of spaces, mobility, and using a few toolbox that we developed. for understanding, again, mobility problem, energy problem, human perception problem. And all together, can we move forward some decision in the community for their social and economic environmental issue? Next slide. So this digital twin system could be identical to what Professor Telemetry marvelous shared with us. For example, for the mobility issue, you can see the right-hand side. There's a button. If you can click, you can see those GPS data showing how humans flow. They are moving around in the city. And we can use machine learning to classify, are they walking, are they biking, driving, or taking public transit using simple algorithm. And you can use traffic modeling to predict where will be the congestion at certain point of time. Next slide. So this is some kind of tool we can bring to the discussion. And can you also click that video? And we would like to combine our understanding about mobility, say how many miles vehicle travel, and how many gasoline you are consuming, and you see how much carbon emission is happening over time. And to combine with building energy, how much energy carbon emission will be produced from building sector. So the nexus of building mobility analysis give us a total idea about urban carbon emission in local community. And the next question is, how do we mitigate the carbon emission to be carbon neutral before 2050, right? So this is kind of the tool and method we can bring to the airport city. Next. So from here, we will begin to look into a community. Those vulnerable community, their resilient problem. So this is one example. There's a community, they're suffering flooding, heat wave attack, earthquake, and it is aging. So this community has a very narrow street. The government has been trying to widen the road because ambulance, fire engine cannot drive into the community if there is an emergency. So we suggest, can we bring in autonomous vehicle? You don't see that like right-hand side bottom. That is much smaller. They can go into the small alley and continue that community social networking, but resolve the problem. And those autonomous vehicle or electric vehicle, when they are not in use, they become battery, urban battery. When there's a blackout, they can help the community for sustaining, maintaining their basic operation. So I think airport sometimes got abnormal situation, hurricane, and can you also come with the kind of resilient system design for the different kind of situation? Next slide. And we would think further. Can we develop a digital twin system as an interface for user, community, stakeholder, policymaker to use them to inform different people about what is happening in the environment. So this is the kind of augmented environment model that we developed in the eco-urban lab. And next slide. And also to look at how human experience urban environment. So when you walk around the airport, walk around the city, can we analyze what they see, what they experience in the sidewalk, public spaces? Can we enhance walkability in the city and their mobility by developing this kind of human environment interface? Say there's a heat wave attack to the city. Can we inform pedestrians to go to avoid the hotspot, to the cooling places, to avoid the problem? So so urban spaces are becoming situational. So human interaction in real time will be very critical for our future smart city. Next slide. So this is the kind of preliminary stage work that we have been trying for airport city. And the future work, we might be able to look into the airport as a globally connected logistics system. And so 110 million passengers stop by Atlanta Airport every year in 2019. Can we utilize those big data, for instance, So there's one example. You can have 24 hours passenger coming in and out the airport, and to see where they are. Are they in the kind of a check-in point? Are they in the concourse, the lounge, or at the gate? The gate. So you can kind of capture those big data over time. And can we also get the data about those passengers? They will be coming in and out Atlanta airport in 1 hour, 2 hour, 4 hour, 8 hours, or 24 hours to understand their destination and to utilize those big data opportunity for the benefit of the airport and the community. Next slide. So with those idea in mind, so we are thinking this digital twin system as a decision platform. We need, how do we connect data, for example, visualize the data and bring in the toolbox of analytics from mobility, energy to resilient issue to help transforming the current community, airport city to be better, right? To be better in mobility, carbon emission, and resilient and so on. So we begin to apply several tools like agent-based modeling to see what if the airport and surrounding would be redeveloped. How would it have impact to the flow of pedestrian, vehicle, autonomous, self-driving car, and so on. As you can see at the top, the two images, outside of domestic terminal of our airport, there's a huge amount of parking. When we have AV system, smart parking system, we could possibly reduce the parking space to be 1/3 or even further. So can we repurpose those land? That is, by the way, that piece of land is similar to Midtown Manhattan. That's amazing. So there's a huge opportunity for Atlanta and the city altogether to reconfigure this, to redevelop this post-COVID-19 airport city. So in which we see digital twin as a new technology would enable community to address some of those important issues. Next slide. So the final two slides, we'd like to conclude a kind of approach we jointly would like to share with our community. Particularly, we have Kirk and Kenneth here. You represent very important entity organization for Airport City. So I'd like to turn it back to Dimitri. Would you like to conclude what approach?
Sure. So these are some artifacts of what is being envisioned over here. So what you see here, very similar to the use case, again, mapped now to the Aerotropolis. You see the horizon from present to near future, midterm, and long-term future, broken now into operating for improved mobility and which is like the present tense, once this is in place, and then the growth potential, which is on the right-hand side. What you see over there is different depictions of the types of data analytics and simulations and visual interfaces that the decision makers can have to determine, the outcomes. And if you click one more time, taking that same idea now, and then showing it over here in terms of the data that has to be gathered. So think about collecting the data, exploring the data, benchmarking, looking into traffic management, forecasting traffic based on different growth or other type of scenarios, explore alternative mobility practices, and that would be under the category of present and near future. If you look at the very bottom, the objectives here would be intelligently monitoring, improving traffic, reduce congestion, and then moving into the more forecasting sense. There might be, again, similar to the campus, there could be new technologies, different design architectures, could be different game scenarios that we want to play, different development of different roadmaps and master plans for the development of the area, and so forth. So this will be all different artifacts that they collectively will give decision makers a pretty good understanding of either the whole or elements of the problem. I'm going to turn it over to Perry.
Thank you, Dimitri. All right, Stephanie, that's what we have for today. Back to you and the panel.
Thank you so much for those informative presentations. So right now I'd like to invite our external panelists to give their thoughts and key issues as well as introduce themselves. Mr. Talbott, why don't we start with you?
Thank you very much, Stephanie. My name is Kirk Talbott. I'm the CIO for MARTA, and we, trying to think, are very interested in this area. It's interesting when you start looking at the long tail of the digital twins, of getting out into the predictive and prescriptive recommendations. Those are exciting, but we today are challenged with simply the descriptive of what's happening and why it's happened on a daily basis. So this is an area that we're definitely interested in, and we're working towards. So it's great to see that this kind of capability can be focused on an area and see what's possible.
Yes, absolutely. Mr. Williams?
Hi, I'm Kenneth. Thank you. Hi, I'm Kenneth Williams, Airport Transportation System Director at Hartsfield-Jackson International Airport, the busiest and most efficient airport in the world. I think this is a great idea of the PRT system that can connect to our domestic terminal as well as our international terminal. Of course, he had in there in the presentation 110 million passengers for 2019. Of course, with COVID-19, we did go down to 42 million, but we are coming back up. We was at the pandemic time, we was at 800 flights. Now we back up to 1,600 flights a day, but we were at 2,700 flights a day. So we're coming back up. The airport is thriving again. The sessions, restaurants, and other business within the airports has opened back up. So we are moving. I think this is a great idea to get the PRT system connected to the airport.
Thank you so much. If anyone has any questions they would like addressed by the panel, please feel free to put them in the Q&A or put them in the chat. In the meantime, Mr. Williams brings up something great that everyone also discussed, which was the effects of COVID-19 on the impact of COVID-19 on this research. Is there anything that you guys would like to add about that really hot topic right now?
I'll take a stab at it. I would say that early on in the pandemic, it would have been nice to have had digital twin capabilities in our operations, because one of our bigger challenges was being able to track in real time and near real time what was actually happening out in the system as we were looking at ridership. What was the pattern of where were people looking to go? Where did they need services? How do we reconfigure in a time of an unknown crisis? So I see a lot of promise in this approach, because while you don't necessarily build it for a pandemic, having something like this in place prior to a pandemic is very, very helpful. That was a key lesson that we learned.
Yeah, and if I can add to this one, the way we were envisioning it, Kirk, was that have an event, like a live event where the models are available and you bring all your decision makers or subject matter experts, if you like, and you start subjecting them to a series of different scenarios. And the COVID could have been a scenario, there could be others. And then they have the luxury of time, right? So they can actually play a lot of games, look at it, play the game that they came up as a solution. And if they find something that they like, that goes as an entry into the playbook. So when there is a crisis, there is a playbook, and you say, I'm executing Directive 49, and everybody knows what to do. It's very difficult to be making things up when you don't know what the problem is, right? That's the vision.
Right. Well, and to your point, in the early days, we didn't know what the problem was, and we didn't know what behavior to plan for. We knew that there'd be a disruption in behavior, but no one had models of what was going to happen. It's similar to the Bridge I-85 collapse that happened a few years ago, right? The whole region went into a chaotic reconfiguration in real time.
Yeah.
That if you'd had the digital model capabilities, like you said, you could plan better for those scenarios.
Yeah. So maybe there are two ways of looking at it. One is that you can have a blue sky type of an exercise where you do try some crazy scenarios like this right ahead of time. The other one is that you have the models available, and when the scenario is more understood or it's happening, then you automatically bring the people back in and say, okay, how should we react to this right now? What are our options?
I think Kirk and Kenny, both of you are handling two amazing complex infrastructure systems, the MATA and the airport. And they are, to a certain degree, they are controlled environment because for the security, safety, efficiency purpose. So these two systems need to be managed. So what if, I think for the issue of post-COVID-19, if we can integrate the big data we capture from both systems and using some AI technique to understand how many people, where they are in near real time, using some biometric scanning, screening, and their body temperature can be captured. And say crowd management, right? We need to have a crowd management in the MATA in the airport, so people will be informed about where they should go to be safer, cleaner. So there's an interactive system that using digital twin. But these two systems, these two entities are operating for their own purposes, right? Is there any way we develop a nexus connecting to this complex system for joint problem? I think this is one example.
I know the airport is exploring all kinds of options to try to keep the customer informed, social distancing. Their Delta Airlines have tested their employees as they come in to go to work, and they are looking at some automated things to get that done. So.
I think one other interesting lesson that came out of the pandemic on this front was, obviously, we've got systems that have telemetry and information flowing, right? And as you make those systems richer, higher definition, higher frequency, you feed that into your twin models. But one of the things we learned was, in the middle of a pandemic, you suddenly have to track information that you never tracked before. We were never in the business of tracking temperatures, right? We were not in the business of when was the last time you cleaned a bus or a train car. So we've had to shift. We track the underlying assets, but we had to shift what are the characteristics and what is the data that we track as well, which was a very eye-opening exercise.
Okay, we do have a couple of questions in the chat. The first question is, how do you QA a digital twin? The graphics look great, and it's great we have the capability these days to produce such a product for simulations and modeling. But how do you verify along the way that the simulation is still realistic and a true twin?
Okay, I can comment on this one based on the exercise from the Georgia Tech Smart Campus. So the very first thing was to do the digital twin based on real data. Okay, so it was a data-driven approach. So we worked side by side with the subject matter experts, from facilities, to actually understand the data, interpret it correctly. Then we went into a phase of cleaning up the data. So the first phase, it was pretty straightforward because it was directly data-driven. When it came to the forecasting, it kind of needed a little bit more attention because now you're forecasting things that don't yet exist. And in fact, the Candida building was our first example where the building didn't yet exist. And Georgia Tech had made a commitment to the Candida Foundation that this will be not just neutral, but it will be energy positive type of a building and water positive. And if we missed the mark, we had to pay back probably about $4 million, from the foundation. So we had to predict its behavior and also make sure that the building is not loaded inappropriately to the point that it will never meet those conditions. All that was done on a forecasting basis. And once the building was created and the sensors were put in place, now we're collecting all the data to go back and validate the model. So when it's a static type of thing, the validation is not particularly difficult. What makes the digital twin difficult is that there is a continuous evolution of the building in terms of its deterioration, in terms of how it's being utilized, the number of people that are utilizing it. So what's making the digital twin is that you have this continuous update. And if there is not a commitment to collect the data and do that, then eventually they start diverging and the model is not accurate anymore.
Okay,
If
great.
Oh, no, I was going to throw in a real-world sample kind of from a different perspective very briefly. We're doing rudimentary work in this space, and we've run into some operational issues where we were getting sensor data that told us one thing, but it didn't jive with sensor data we were getting from other sources. So one of the things I would answer to that is, in a real-world operational model, you need to have multiple sensors that are on independent systems that you can correlate so that you can tell when one system is off, right? Because a lot of data errors come from bad sensors out in the field.
Yeah. And there are a lot of bad sensors for sure. So to Kirk's point, this task is called data fusion, right? So you are triangulating, if you like, from multiple sensors, try to identify whether the information that is coming in is flawed. And we had the same experience. There was a lot of information that was flawed. In fact, there was one building on campus that the entire HVAC system was working for 2 years, and it was unnoticed to the fact no one noticed it because most of the people were transients. They were not really living in this specific part of the facility, that the HVAC was not doing anything, was not wired properly. It wasn't taking out any heat, So again, it's an obvious thing to fix after you can see it in the data, and then you can go and inspect it.
Great. We have, I know we're getting close to 1 o'clock, but I was hoping to get in one more question. We have one more. It says, Dr. Yang, you mentioned an Aerotropolis model that includes new mobility services such as autonomous vehicles. Can you discuss how and where urban air mobility, drone taxis, would potentially fit into this model, allowing for other mobility options?
Yeah, I think a lot of future mobility would reconfigure our urban form and city dramatically, right? Like AV can be so small, pedestrian friendly. The way between the sidewalk and the public spaces will be much more flexible. So imagine 2050, some area in some city will become totally car free. I think airport, city, and surrounding will be has a great potential to become the laboratory for testing this new technology. So I think we need to combine those new mobility issues and see how we benefit community and the public sector like MARTA and airport and so on. And for instance, car parking, right? Airport has been relying on parking as a main revenue. Can we come with some new business model to repurpose those parking and become the airport hub? And there's a new citizen that might emerge from the adjacent land of domestic international airport, like Hong Kong, Amsterdam, Singapore, and so on. And MARTA, the ridership increase, will benefit from that increasing ridership. And airport would become a new urban public spaces. New mobility and new future development might be integrated all together. And that's what I have.
Yeah, and maybe what I can add here is that this is perhaps the one thing that really links to aerospace compared to everything else. So we have been studying the urban air mobility now for about maybe 10 years. We have originally done studies for NASA for the San Francisco area. And when we saw this opportunity, we had actually some of our students deviate to solely look at that portion, especially when you look at the, let's say, the Atlanta metropolitan area plus suburbs is about 100 miles across, So you can definitely see some solution where people will be coming to the airport from far away areas rather than having a second airport, which was a proposal at some point in time that probably financially doesn't make a lot of sense, And then, of course, there is the cargo UAV. That's another area. We just finished a study yesterday for NASA. It was presented to them with LMI. And the idea there was it was a big net on all the possible uses of cargo UAV and how autonomy can play into this mix. So every time you're thinking of futuristic projects like this, you can also think of other modes of transportation that could be coming in to help.
Yeah. Can I have one final remark?
Of
As
course.
an urban designer, I like to dream or envision about what the future would look like. Say PRT, people, personal rapid transit, the kind of smart part. They are on demand. So they are healthy part as well. When everyone go into the small vehicle, you got health screening and you got security check. You can check in and the people mover system will draw you all the way to the gate. So maybe there's a future system so pedestrian friendly. If I stop over Atlanta airport for 4 hours, 6 hours, I can take that small vehicle to College Park to do shopping, resting, interacting, meeting with other people. So it's an urban center. It's a future city. There's a huge amount of opportunity. And the MARTA, by the way, connect that airport hub to the much bigger city area. And that would be a possible sustainable urban future.
Great. Thank you so much to our panel for their presentation, comments, and thoughtful responses. And thank you all so much for joining us today. Please continue to monitor our website for upcoming Smarter Together webinars, and we look forward to seeing you all again.
Okay. Thank you.
Thank you.
Thank you.
You.